In this video, I'm going to talk about the tetrahedron states, which is a visual tool to show the analogs between energy domains. The first thing we're going to talk about is going back to physics and the conservation of energy. In the conservation of energy, we have a system, and it has some kind of energy in it. And that energy could be kinetic energy or some form of potential energy. Sometimes people think about it as kinetic energy as thermal energy, but at this time we're just going to worry about kinetic and potential. Going to the idea of conservation energy, the energy into the system is equal to the energy out, and that'll be equal to the change in energy of that total system. Okay. So we're going to start off with definition of energy. Energy is the ability to do work. And so we've used mechanical energy from our physics in high school, and the definition of work in the mechanical domain is force times distance. We also think about kinetic energy as 1/2 mv squared. This also can be written as 1/2 momentum, which is mv squared divided by m, and it would result in 1/2 p squared over m. The other form that we often think about for potential energy is mgh, and the h is the height of an object relative to a reference point. Another form we might see is potential energy is equal to 1/2 kx squared, which k is our spring constant. We also know some of the other terms. We know Newton's second law. Force is equal to mass times acceleration, and that could be seen as a form of m dv dt, or we also might see it as dp dt, the change in momentum with respect to time. And that's actually how Newton described it, is that force is equal to the change in momentum with respect to time. Another term we'd also think of is Hooke's law. And this is the relationship between force in a spring relative to its displacement. Sometimes we'll see it as negative kx, and that's just going back to our idea of the system, we have the change in energy of the system is equal to the energy in minus energy out. One thing about this is we can't really deliver 5 joules of energy into the system and then 5 seconds later receive that system. It has to be instantaneous. This is very similar to the idea of continuity principle of mass coming in and out of a system. So we're going to go ahead and write that this is the derivative ddt of the system, and the time derivative here of the energy. And this also another form that we might see it is written as E dot of the system, where the dot is the derivative with respect to time, minus E in, or is equal to minus E dot in minus E dot out. What is the time derivative of energy? That is power. And power by definition, or another form of definition, is equal to work divided by time. Or divided by time. So, or, and we've gone back to, we've talked about work as being force times distance. And so this could be written as power is equal to force times distance with respect to time, assuming that energy is not we're going to assume for right now that force is constant, and so the distance over time is r would be force is equal to times velocity, and that is power. So stepping back, so if we move back to our connections with the power in the electrical domain, one of the, again, terms that we use quite often for power in the electrical domain is P is equal to I, the current, times voltage. And we'll see that there's a similarity here. And this is, we'll see that we have voltage as a potential and force as a potential. We have some kind of function of with respect to time, derivative with respect to time. We have current, which is the charge with respect to time. And we have velocity as a position with respect to time. You might also see this in different forms. So we might see this as I squared R, or V squared over R. And these connections are just back to our Ohm's law, which is V is equal to IR. Okay. At this point, I'm going to pause and not talk about the kinetic and potential energy in an electrical system, but I'm going to start doing a reference there. Again, this is going back, even though you might be an electrical engineer, you've spent more time with physics in the mechanical domain, going back to high school and stuff like that. So, so with these power, we're going to set up two power variables. The first is going to be effort. Second one is going to be flow. And as we can see, we'll see similarities between the electrical and mechanical domain. So for the mechanical domain, electrical domain, we're going to see effort as force, and there'll be capital F. In the electrical domain, we're going to have voltage, or volts, and that'll be capital V. And flow in the mechanical domain will be velocity, and that'll be script V with the hat over the top. And we're going to have current. I use I for current, and so it's current, and script I for current. So again, if we take power, that's going to be equal to force times velocity in the mechanical domain, and voltage times current in the electrical domain. What are the units here? the units of power are going to be watts, which is a joule per second, which is also equal to a Newton meter per second for both systems. Now I'm going to introduce some other things. In the mechanical domain, we have inertia. An inertia term is going to be mass, and the units are going to be kilograms here. In the capacitive or storage component, we are going to talk about the spring as being able to store energy. And so these are, spring and the term is, we're going to use the spring constant here, K, and the units are going to be newtons per meter. These two elements store energy. Okay. The final term we're going to talk about is resistive element. And for this, there's different forms, but we might see this as just R. We might also see it as B or C. We'll not worry about the units at this time. Okay. Again, I'm not going to, we'll come back and look at the inertia, capacitive, and resistive elements in the electrical domain in a second. But I'm going to show you a graphical tool to allow us to remember some of the relationships we see and make those connections between energy domains. So we're going to talk about a mechanical system, and we're going to look at the tetrahedron of states. So tetra meaning 5, so we have 5 edges here. Okay, the top and bottom are going to be our power elements, so we have effort, and this is little e, and for the mechanical domain, where it's going to be force. In the bottom domain, it's going to be our flow, and that's going to be lowercase f, and this is going to be our velocity. The two other things we're going to talk about are our energy variables. The energy stored in a mechanical system can be described by the momentum of the system, P, and the charge or displacement on a spring. And those will be going to on our left and right hand sides of our system. So we're going to have P here and X. Now all of these lines represent a relationship between the systems. So how does displacement what's the relationship between displacement and flow? That is the time derivative, d dt of x. Okay. Again, going back to Newton's laws, he also said that the time derivative of momentum, d dt, is our force. Momentum, we said, was mass times velocity. So this is going to be, we're going to have our inertia term, which is our mass. And so we take our flow term times our inertia term to get our momentum. And then on the other side up here, we're going to have our spring stiffness, so our K. And so if I take my displacement of the spring times K, I get an effort. And then the resistive element is the connection here. This is just a kind of a graphical representation. The great thing about this is I can actually if I know this terms, I can transfer it into the electrical domain, and we will do that in the next video.